Have you ever watched a pendulum swing back and forth, or a ball bounce up and down, and wondered, where does the energy go when the motion slows down? Well, welcome to today's session on one of the most fundamental principles in physics, the principle of conservation of energy. It says energy can neither be created nor destroyed. It only changes from one form to another. That means if a body has a certain amount of energy, say potential energy, and starts falling, that energy transforms into kinetic energy, but the total remains the same. Whether it's thermal, chemical, or mechanical, the total energy in a closed system stays constant, provided there are no losses to the surroundings. This powerful idea underlies everything, from power plants to your body metabolism. Now imagine holding a ball at a height. At this point, the ball has maximum potential energy, stored energy because of its height. As you release it, the ball starts falling. What happens to that stored energy? It begins converting into kinetic energy, or the energy of motion. The higher the ball was to begin with, the faster it falls, and the more kinetic energy it gains. But here's the interesting part. The total energy remains the same throughout. At every point during the fall, the sum of potential and kinetic energy is constant. That's energy conservation in action. Energy changing forms, but not disappearing. Let's verify this principle with some equations. From our kinematics, we know v squared equals u squared plus 2as. Since the body is dropped from rest, u is 0. So we get v squared equals 2g into open bracket h minus x, close bracket. Now kinetic energy is Ke equals 1 divided by 2 into m into v squared. Substituting the value of v squared, we get Ke equals m into g into open bracket h minus x, close bracket. At the same height x, potential energy is Pe equals m into g into x. So total energy becomes Ke plus Pe equals mgh, and that's constant at any point of motion. A simple but elegant proof of how energy remains conserved in freefall. Let's break this into 3 positions during the fall. At the top, height equals h. Kinetic energy is 0 because the body is at rest. Potential energy is m into g into h. Total energy, m into g into h. Now at an intermediate height x, kinetic energy is mg into open bracket h minus x. Potential energy is m into g into x. Add them, and again you get mgh. And finally at the ground, potential energy is 0, but kinetic energy is m into g into h. So again, total energy is the same. In every case, the body's mechanical energy remains unchanged. That's the beauty of this principle. This principle isn't just theory. It's behind so many practical systems. Take a hydroelectric dam. Water stored at height has potential energy. As it falls, that becomes kinetic, which turns turbines and finally becomes electrical energy. Or picture a roller coaster. Climbing up is storing energy, and as it zooms down, that energy gets released as motion. Even a simple pendulum clock works on this continuous transformation between potential and kinetic energy, swinging endlessly, driven by gravity. Energy isn't lost. It's just transformed into forms we can use. Now in the real world, we do face complications. Let's say a ball is dropped from a height and hits the ground. You hear a thud, right? That sound and the little bit of heat generated, that's energy too. In this case, some of the mechanical energy was converted into sound energy and thermal energy due to friction or air resistance. But the total energy, if you account for all forms, still remains conserved. That's why engineers always consider non-mechanical losses while designing machines, turbines, and even spacecraft. So yes, even when things seem to slow down or disappear, energy isn't gone. It's just elsewhere. The principle of conservation of energy tells us that the total energy in a system stays constant, even when it changes from one form to another. For example, in the case of a freely falling body, potential energy is gradually converted into kinetic energy, but the total energy remains the same throughout. Mathematically, This is shown as the sum of kinetic and potential energy being equal to m multiplied by g multiplied by h at any point during the fall. This principle is not just theoretical, it applies universally, whether in natural processes or technological systems. By understanding and applying this concept, we can design more efficient machines, reduce energy loss, and create smarter energy systems for the real world.